Alright, hell yeah. So we have material mechanics, and this is a 1-star problem, you know what I mean? And I probably don't have the skills just to nail this. So this might be a pretty slow video, but I think that's, I don't know, some of my best are probably the ones where I have to figure it out. You know what I mean? Because this deals with shear forces and bending moments. And I swear it's just like, what is a shear force? Sometimes I have no idea. You know what I mean? So, but I think when it comes to material mechanics, sometimes it's useful to break things down at the molecular level. So here is, you know, maybe a chunk of steel, and this is 2 rows of molecules, like atoms or molecules. And what we're going to do is we're going to apply a force. You know what I mean? I guess we're using P for forces. And then we're going to apply a force P in that direction. And what our objective is to take that and make those 2 molecules move across each other to the point where, you know what I mean, they kind of just give up and break away. And we know that if we have 2 molecules this way in material mechanics, where if we pull on them, all we really have to do, if it's steel, all we have to do, and this is like the length of that molecule, we just have to increase the length by 0.2%. You know what I mean? So that's a 0.002. That's going to be the fraction of the entire length. So if we know this length right here of 2 steel molecules, you know, put together, we just have to increase the length of them by 0.002. And basically steel is iron, you know what I mean? So basically you'd have 2 iron molecules, you know, whatever those would look like, the size of those. And you're just trying to increase that length by that much. That's kind of the principles of material mechanics. But shear is kind of an interesting one. So I don't know, let's take 4 of these molecules. And same thing, down and then up. What you're doing is you're at some point... and, you know, this is such a tiny amount. Like, you know, I mean, we're not taking these molecules and turning them into a 45-degree angle. Like, steel cannot handle that. Now, steel can, like, you know, like, if you have a long enough specimen and then you do this, you might be able to get a 45-degree angle. But it's because you're, you know, for every stack of molecules, I mean, you're just hardly... moving them, and yeah, so you might be able to get a slope going. Oh man, I hate when I start to say stuff that's probably not true, so just disregard the fact that the angle could be, you know, high at all. So anyway, I don't think that's actually true. But okay, let's get back to kind of the problem. So we have this idea that if we apply you know, forces, it's going to cause these molecules to move. If they move a certain amount, you get break. And if you just have 4 molecules and apply a force, well, like the connection force between those 2 is the only thing that's holding it together. And then so the force that you have to apply is much less than if you have a bunch of these molecules holding themselves together. You have to apply more force to make those line of molecules move. Okay, so hell yeah, so it's kind of just shear force in a nutshell, and we kind of understand now what that means. And then bending, I think bending is pretty straightforward, even though, like if I have, like let's say I have this ruler, and then I apply a force in the middle, you know what I mean, just kind of with my finger. I'm not actually applying pure bending. I'm applying a point load in the middle, so it's a combination of shear and bending, compared to if I just take this ruler and then make a couple, like a twisting motion, a torque motion. This applies pure bending to the ruler. But if I have a point load in the middle, it applies a combination of shear and bending at the same time. All right, so okay, so I think what's going to help us is using free body diagrams. All right, sorry about that. Yeah, so what we're going to do is we're going to tackle the free body diagram, and we might make a simpler problem. So I think it might be useful just to start with a beam supported at two ends, and then just a load in the middle called P. And so we have L divided by 2 on both sides. And now we're going to take a look at this. To do a free body diagram, we basically chop whatever we want, but we're going to chop that outer space. So it's best to chop the entire thing. So we're going to come over here, and there we go. We have the entire beam, and now, like, I think it's kind of cool. So what we're going to just pretend like this thing is just floating in outer space. If it's like the only thing in the universe, there's no forces on it at all. In this problem, though, well, I guess it doesn't matter. Like, yeah, this beam does have a mass, a simple beam. I mean, you would have to put that in, but I don't think it's going to change the problem around, you know, have this beam having a mass. Whether it's a massless beam, a very lightweight beam, and these are like very substantially heavier, that's not going to change the problem. I don't think, but yeah, let's put it in there. So we're going to have a mass of the beam due to gravity. So that's going to be the first force that we have. We have that mg. And then the other thing that we see is that on our diagram, we have we're going to apply a force P. And so if this thing's floating in outer space, and we know that we're applying those two forces, this thing's going to be traveling this way. And so we have to balance them. We have to have some sort of forces up that are equal to these and opposite. And so those are going to happen at A. So we're going to have AY, and then and all our forces are just going to be in the we're not going to have any normal forces, I don't think. So yeah, so I'm just going to call this force A, and I'm just going to call this force B. Cool. And so we have sum of the forces in the y direction are equal to 0. We're basically using F equals ma. We know that we have a mass, and we are applying forces. And if we do have a net force, like I said in the beginning, this thing is going to be traveling this way, and it's going to increase in speed. You know, it's going to have an acceleration. But by observation, kind of back on Earth, when we set up this experiment, put a beam here on two supports, and then put a heavy weight on it, hey, we have zero velocity. This thing's not moving this way or that way. Cool. So it means that the sum of the forces in this direction, let's say the y direction, have to equal the mass times acceleration in the y, and that acceleration is 0. So we're going to have the sum of the forces, and we're going to add them up. So we're going to have A plus B minus P minus mg, and that's going to equal 0. Cool. And so that's kind of one equation that we have. Now we could sum the forces in the, and we will. This is a roller, so we're only going to have a B, but we are going to have an AY and an AX. But we're gonna see if that has any, because if we there is no other forces. You know what I mean? There's no forces in any other direction, so this is going to be 0. Yeah, because we can just do that right now. So now we're going to sum the forces in the x direction, and those are going to be 0. So we have the only force is AX. That's the only force I see in that direction. That's going to be 0. Cool. So this was the y, this was the x, and now we need to do moments. So we're going to sum the moments. We can sum them about any point. And what that says is that if I have this thing floating in outer space, and then I have a force over here, and then a force over here, well, I know that the forces are balanced. There's no force in this direction, so it's not traveling this way. These are balanced, so it's not traveling this way, but you can obviously see this thing's going to spin. But then if we say this is back on Earth like a beam that's not spinning, then we know that these two forces are going to cause a spin, so we must have other forces that balance that tendency to spin. So this is creating a moment. We have a distance here, and so the moment that this creates, magnitude is F times D. And And let's slow it down because we're going to have to maybe pick a center. And what we would say is that the sum of the moments about this center are going to be 0. And so let's start. We're going to go over to this force. This force is a distance d divided by 2, and then we run into that force. It's going to cause it to spin this way. That's going to be the negative direction. So we have negative d divided by 2 times that force. Now let's do this force. From this point, that's going to also cause it to spin. My thumb is down. It's going to cause it to spin in the negative direction. So we also have negative d divided by 2 times f. And I always do this because I swear this is the definition of a couple, where you have the same magnitude on both sides separated by a distance. And this is the definition of a couple, where the moment of a couple is just d times f. And so that's what we're seeing right here. So we have this is the moment d divided by 2 times f minus d divided by 2 times f. This is just d, negative df. So we have the magnitude of the moment is df, and it's in the negative direction. Cool. So we have to balance that with a moment in the opposite direction. And so we could just apply a moment. You know, I mean, we could attach something right to the middle of this. You know what I mean? And then start to well, let's see. So if this is going this way, yeah, we could attach something at the center of this and torque it the opposite way. And this moment right here would have to equal df, because we'd have negative df plus that moment has to equal to 0. That's the equation, and we have that moment is df. So it's positive df. Cool, so that's what we're going to do right here. And we can sum the moments about any point. So let's say we took the moments right here about A. We would do sum of the moments about A. And we would say we have, so disregard this moment for a second, and we would have this force times the distance. So we would have negative FD plus some moment at A, and that's going to be equal to 0. And this also shows the definition that this moment can be placed anywhere. Attaching something here and then applying a torquing motion is the same thing as attaching something here and applying a torquing motion at A. And that's what we see. So we see the moment at A is going to be FD. And let's do it one more time. We're going to sum the moments at B is equal to 0. So we have this force. It's going to be a negative FD plus, some moment. And that's going to equal 0. And that moment has to equal FD. And so yeah, somewhere on here we have to have a moment. Okay, hell yeah. And let's slow this one down because I think I have a cool way to explain this. So again, we're going to take this little chunk of beam and then pin it to outer space, and then we start to apply, a bunch of different forces. Let's say we got that going on, and we know from observation down on Earth that it's not moving. So the fact that we put this in outer space and apply all the same forces, it's also not moving in outer space. So that means that one, it's just not moving, but two, you can pin this thing at any point you want to. So I could put a pin and then thumbtack it up against outer space, and it would still not spin around that point. I mean, it's kind of redundant, but we're saying it's not spinning anyway with these forces applied. But that also means that I can put a thumbtack anywhere and thumbtack this thing, and I know that it's not spinning. Now, if this thing was moving and I applied forces and I applied a thumbtack, well, it would spin around wherever I tacked it because the forces would be unbalanced. But when we have statics problems, the forces are such that it's not causing any moment about any point on this. So we could literally tack it anywhere, and then we could use that point, let's say the point O, and then we could see that we have a force over here, that distance, that's going to cause a negative moment. This one's going to be positive, and then this one is going to be negative. And these two that are negative are going to balance this one that is positive. You know what I mean? So that's kind of what happens with the sum of the moments are equal to 0. But I mean, I don't know. It's kind of mind-blowing to me. It's just like, well, how do I explain that to myself, that I can take moments about any point? And I think this is a good analogy. It was you cut it out and put it into space, just free floating there with all those forces attached. It's not going to spin. It's not going to move in the x and y direction. And so technically you could take a thumbtack and pin it to outer space, and obviously it's not going to move about that point. Just by definition, it's not moving anyway. But that point, you could make it a point that could move, and you could sum the forces around that point that would cause it to move around that point. But then you would see that those forces, might be balanced. I mean, this is going to cause a negative. Well, in this case, hell yeah, this would cause a spin. You must have some sort of force to counteract. That's a negative again. So how do you do a positive? There you go. So you must have some sort of force in the positive direction to cancel out all of those. So that's kind of just a visual representation that you should always just kind of have in your back pocket. Because then you can pick any point on here. And you can pick a point where it's just like, if I pick the point right here, these forces going through that point aren't causing any moment. So that's a great place to pin, because now I can see that these two forces, mainly the force that we're applying, is causing a torque, but that torque is only half the distance away, and then so this has to be applying a torque. There has to be a number on this force at twice the distance that's causing it to spin the other way, but balanced. So if this is a negative moment, this is going to be a positive moment, and this because it's twice the distance, it's going to have twice the leverage, and this force, the magnitude of this force, is going to be half of that P. Cool. All right, hell yeah. So that was a long way to get, just the simplest, simplest problem, where you're just like, oh, okay, the sum of the moments, and I can choose any point. I'm going to choose this point A. I'm going to say the sum of the moments about point A are 0, so let's sum them up. We're going to have P, and then L divided by 2 is that distance. That's going to be a negative moment. And then do I have any positive moments? Well, yes, this reaction at B. So we're going to have plus BL. This is going to equal 0, and now we can solve for B. So we're going to take this to the other side. So we're going to have BL is equal to PL divided by 2. And we can just factor out an L. And then we can see that B is equal to that load divided by 2. So B is equal to 1/2, B is equal to 1/2 P. All right, hell yeah. So that's if the load is right in the middle. All right, let's see where we want to go from there, because I think we still want to do more free body diagrams. So so we're on a roll. We can chop this beam out of outer space. We can now let's neglect the fact that this beam has mass, and now let's incorporate maybe both of these. I think I can handle that. So we have P and then 2P. I don't know, maybe I can't though. And now we're going to have A, and now we're going to have, I don't think I should have done this right now. But anyway, A and B. We're not going to have any forces in the other directions. And so when we sum the forces, when we sum the forces in the y, these two, so we're going to have 3P, so you should be able to see that. We have 3P is equal to A plus B. Sometimes just visually, I think it's better to do this visually than, lay out some of the forces are in the y is equal to mass times acceleration in the y, that's 0. So, and then sum the forces. You'd be like A plus B is equal to minus P minus 2P is equal to 0. So that's the full equation. and we have A plus B minus 3P is equal to 0. But you can just see that if we have this thing floating and we have 3P down, we have to balance it with these forces up. Alright, so now we're going to get into our moment equation. I guess we do need to include this x and this d. And for the time being, we could say this x is just L divided by 2. That'd be maybe a good place to start. Cool. So we're going to sum the moments about A. We're going to do that same thing. So sum the moments about A is going to be 0. And then so we're going to have this B. That's going to be a positive moment of BL. Now we have both of these. We're going to have this first one is going to be a negative. And we're going to have P times, and then the distance over. Let's just say that's L divided by 2. Cool. Now we're going to have this one. This is going to be a negative moment. If we start at A, we're going to push our finger. We're going to use the right-hand rule. We're going to push our fingers over in the direction of this force, sweep our fingers down, and that's going to, basically it's going to cause a rotation that way. With the right-hand rule, it's a rotation. My thumb is pointing in the negative direction, so that's a negative moment. So we have this force negative 2p. So we have minus 2p, and it's a distance away of L divided by 2 plus d. All right, sweet. Now, from our problem statement, we probably should just, put numbers to this, but I guess we're not. But we have, so we have an equation here, we have an equation here. And so here's our other equation. This is the equation in the y. The things that we do not know are a and b, and we have b right there. So we do know the load P, that's going to be given. We know the length, we know this distance D, and so everything else is known. So we can solve, and this equation just solves for B. So that's kind of cool. The sum of the moments about point A, solve for B. So that's pretty cool. And heck yeah. So let's do that. So we're going to say that B, I'm going to do this all at once. I'm going to take these two things that are subtracted. I'm going to bring them on this side. I'm going to add them to that side and then divide by L. Because they both have an L in them, I'm just going to bring those over there and call it good. So we're going to say that's positive 1/2 P right there minus 2P times 1/2 plus D. Cool. So that's my equation for B. And might as well, holy hell, this thing is going to get out of hand using letters. I don't know. I think just throwing numbers at it is the best way to go. So in my calculator, P is 10 kilonewtons. I'm going to store that as alpha P. We have D, 2.4 meters, stored as alpha D. And then 12 stored as alpha L. Cool, so we got 0.5 alpha P minus 2 alpha P, 0.5 plus alpha D. Okay, and this gives us a force of, oh, so yeah, we probably royally messed up. Where did we go wrong? Oh, this should be an addition. My bad. Holy hell. Yeah, it's adding both those. So just a little sign. I hate negatives. All right, so we have 63 kilonewtons. That's going to be the force at B. And then we can easily just throw that in here. We can rearrange this to solve for A. So A is 3P minus B. So sweet. I'm going to store the 63 as B. And then up here, 3P minus B. All right, so why am I messing this up? Oh, 3P is only 30 kilonewtons. So yeah, where are we getting, why are we messing this up? Alright, holy Toledo. Let's sum the moments from A just using numbers. So we're going to have whatever B is. So we're going to have B times 12. Cool. And then we're going to have, P is going to be 10 kilonewtons. So we're going to have, so B is going to be a positive force, and then we're going to have minus. Oh, and the other thing you can do is if your sum of their moments add up to 0 and you have positive moments and negative moments, you can just make those equal to each other. So here's my positive moment here, and then here's my negative moments. Because I have this equal to 0, I could just say, hey, let's just take the negative moments over there, and then let's do that. So we're going to have 12b. These are my positive moments. That's the only one. These are negative moments. And so we're going to have 10 times half the distance. That's 10 times 6. So that's going to be 60. And then we have this 2p. That's going to be 20 times 6 plus 2.4. So 2.4 plus 6 times 20. And so that's going to be plus 168. Yeah, I must have done my calculation wrong. Oh, you know what? Yeah, no, I can't just factor out a length because I have a length right there. So my bad on that. So I had to keep that in. So if I did that, I would have D divided by L. And that makes sense because my unit, you can always check your units. If this is going to be in newtons, okay, I have force in newtons or kilonewtons here. I have a force in kilonewtons multiplied by this must have units of, these must have dimensionless units, and since I have a distance here, I got to divide by L. So let's just go back to our equation. It's always good to figure out where you made mistakes. So we're going to go back to that equation. And so we're going to go 0.5 P plus 2P 0.5 plus alpha D divided by L. Sweet. So this is going to give me, B is going to be 19 kilonewtons. So now I come up to here and we can do 3P minus 19. And so A is 11 kilonewtons. So holy hell. But let's continue doing this way, you know what I mean? Because we had 12, well, this distance B, that's going to be the force times the length is 12. And then this was going to be 10 times the length of 6. So 10 times 6 is 60. This is going to be 20 kilonewtons times the length of 2.4 plus 6 times 20. That's going to be 186. Sweet. So these have to balance. So we're going to have 60 plus 168 divided by 168 plus 60 divided by 12, and that's going to give B of 19 kilonewtons. All right, so we have another check on reality. Holy hell. All right, sweet. So I guess from that, what we have found is that A and B are going to be 11 kilonewtons and 19 kilonewtons. Cool. Now there is a scenario where when this thing is over A or this one is over B, we should account for that scenario as well. So let's just do that like right now. So we're going to put P here, and then we're going to put 2P right there. And now let's find reaction A and reaction B. And we know that we can just sum the moments, so we're going to sum the moments about A. We're going to have 20 times 2.4. That's going to be a negative moment, and then it has to add to a positive moment of B times 12. And that's going to be equal to 0. So we can solve for B. Bring this to the other side. That's going to be 20 times 2.4 divided by 12. So in this case, B would be 4. Sorry. Oh, man. B would be 4 kilonewtons. And then A, using our equation up here, would be 3 alpha P minus 4. So A would be 26 kilonewtons. Cool. And would that make sense? I mean, basically, we're going to have this one. I mean, we're for sure this 10 kilonewtons is going to be all absorbed by A. But the fact that this one is so close, what happens, and I should kind of go over this, is if you have a simple beam and you put the load right in the middle, hell yeah, both people like having to hold this beam with like the weight in the middle, if you got a couple people here, then they're going to have to take equal load. But then if you do the extreme of like, hey, let's put all the load over here, and then you still have a beam, and then this person still wants to help, like, hey, like this person basically has to carry all the weight, you know, and the opposite would be, you know, if the weight's over there. Now this person has to carry all the weight. This person doesn't have to carry any of the weight. And so and so this is over here. This is 100% of the weight is carried by that person. This is 100% is carried. This would be 50%. So now this is always a good one to do, is kind of figure out why this is the case, or how to let's see. So if I do a beam, and we're going to divvy it up into four spots. So we're going to put the load right there. And we're going to sum the moments. So this is going to be A and B. And we're going to sum the moments at A. Those are going to be 0. So we're going to have, and I'm just going to say this is 1 meter. Sweet. So we're going to have some force at B times 1 meter. That's going to be a positive moment. That's going to equal the negative moments, which is going to be this P times, 0.25 meters. So we can see that B is going to be 0.25 P. And you can say that this load B is going to be 25% of load P. So if you throw a load on here and you're a person trying to carry this side, you're only going to have to carry 25%. So now let's sum the moments at B. And so we're going to have a negative moment of A. So we're going to have A times 1. That's our negative moments. We have a positive moment P, so that's going to equal our positive moments. And we're going to have this distance is 0.75 P. Alright, booyah. So you can see that this person will have to carry 0.75. That's 75% of load P. Cool. And that's just from this distance being, and the only thing that you have to know is that just visually, like hell yeah, if the load's over here, this person's going to have to carry more. And this person's going to have to carry, hey, 75%. There's 75% of the beam over here. So that's kind of how you do it. There's 25% of the beam right here. This person is going to carry 25% of the load. So, and I think that it is useful to do, is to kind of get used to that. That was that, the rolling discs problem, where you had the 2 rolling discs. This required you to find the center of mass. And this was 5M and this was 1M. And then so, yeah, let's do that. So you have, I don't know, is that a good representation? Well, let's see. So, and I don't know, maybe this was 4 and this was 1. I think that was the case. This was 4 kilograms and this was 1 kilogram. And so it's kind of the opposite, because let's see, how would that be? The total weight would be 5. So you're basically having a beam where you're putting, at some point you're going to put a load of 5 kilonewtons on the beam. And you're going to do so where one person has to carry 4 kilonewtons and the other person has to carry 1 kilonewton. So this is just good for me, because what percentage of like how much percent is this? So we know the load is 5. What percent is this person carrying, and what percent is this person carrying? Well, this person is carrying 1/5. Oh, that's 0.2. That's 20%. So if this person is carrying 20%, this must be 80%. And that's what we find. 4, this number divided by 5. And if you can't do fractions, like even 1/5, like don't do 1/5, do 2/10. You know what I mean? Just easily bump the denominator up to 10. Same thing here. This is going to be 8/10. Cool, that's 80%. That's going to be 0.8. All right, hell yeah. So cool. And then, so where do you put the load? Well, you would have to have, if this is the length of the beam, and I want this person to carry 4, well, I must have to put this load closer to this person, and I would have 80% of the beam over here and 20% of the beam over here. So we're going to have 0.8 L there and 0.2 L there. Sweet. Alright, hell yeah. So now we can go back to our problem. So if we have this load over A is gonna take all of that load. But we do still have this 2P load, which is a distance of 2.4 meters, and this total length is 12 meters. So what's the percentage of this distance? So that is 2.4 divided by 12. So we have 20% of the beam here and 80% over here. So that was a pretty cool representation that we're going to have. So of this 2P, of this 20 kilonewtons, 20%, B is going to have to carry 20%. So I don't know what 20% of 20 is. I do know what 10% is. That's 2. So this is going to be 4 kilonewtons. And this one is going to have to take 16 kilonewtons. Plus that initial P. So this is going to be 26 kilonewtons. 26 kilonewtons at A, 4 kilonewtons at B. And we have 3P total, so cool. So now we're getting kind of used to the problem. We have 30 kilonewtons, 26 and 4, and so that's what we have here. So now let's do it on the other side, and now we can just kind of intuitively do it. So we're going to have 2P at B, and so B has to take all of 2P. You know, it's like directly right over, but we're going to have this 2.4 meters, and then we have P. And so this is going to be 10 kilonewtons, this is 80%, and this is 20%. So 20% of 10 is still, yeah, that's 2. So yeah, I can do that. That's 2 kilonewtons. 80% is 8 kilonewtons. So whatever, B has to take 2P, which is 20 kilonewtons, plus the heavier side, plus 8 kilonewtons. So we have B is 28 kilonewtons, and A, in this case, well, you can just say that there's 30 kilonewtons, and you have to take the remaining 2 kilonewtons, or you can see that that's going to be 20%. 20% of that 10 kilonewtons out there. All right, sweet. So those are the scenarios. So let's write those in. So if the thing is over here, A is going to be 26, B is going to be 4. If the thing is over here, we have holy hell. 2P is going to be 20 plus 80%, so that's going to be 28. So B is going to be 28, and then A is going to be 2. Cool. And that's the only, that should be the only ones that I'm, well, now, if, what did we say? If this thing was, I mean, we solved for it, so we might as well use it. We solved when this distance was 6 meters. That A was 11 kilonewtons, and so we had 30 minus 11. Oh yeah, and B was 19. So I guess we could throw those in there too. So A was 11. Yeah, 11, and B was 19. And visually we can kind of see that. Okay, sweet. Because this is the one where this distance was 6 meters, and this was 2.4. That was the one I was kind of curious about, because we know that A is 11, B is 19, And then I wanted to kind of take some free body diagrams. So what I wanted to do was chop, and let's just chop a couple, let's just chop 3 meters off this. So if we're saying this was kind of at the halfway point, we're going to chop 3 meters. So we're going to take this little chunk, and we chopped it. So right here where we chopped it, we really don't know anything going on at that point, but we do know there can be a normal force, there can be a shear force, and then there can be a moment. So those are the things that we can always add those in. And I shouldn't have drawn it even like that at all. Let's just draw it without that, because it's kind of interesting just to know your cut is going to be right there. But then add the things that you do know. So we do know the reaction at A, so we know that we're going to have 11 newtons there. And if you treat this like it's a mass floating in outer space, and you just put a force on it, because F equals ma, means that we're going to have a change in velocity of this thing in that direction. But then when we go back down to Earth, it doesn't matter if we chop this whole beam out, like everything, nothing's moving on this. So whatever we chop out, it's going to have 0 velocity. So we chop this out. It must mean that we have the forces must balance. So at somewhere we must have a downward force of 11. Now the only places that we can actually get forces are where we chopped it out, because we already see that we know that we have a force here at A. Cool, but there's nothing else touching this beam, in this area at all. So we know the only place that can have forces are where that cutout is. And I think a concept like that, I don't know, I think like professors just tell you once, and then you're just supposed to like nod your head and be like, oh yeah, no duh, I get it. But I don't think that's the case. I mean, just cutting something out, I don't know where you get all these magical forces, but if you do it from this perspective, that you know that there's a force at A pushing this chunk of material up, and the fact that you can cut out, just theoretically, make a free body diagram of any chunk you want, and then if you place it in outer space, put this 11 kilonewtons on, well, it's not moving, so there has to be an 11 kilonewton force there. So booyah, so now we're getting into it. So now the forces are balanced, but this 11 kilonewtons isn't right here. If it was right there, then it would be nice and balanced. But because it's over here, this is going to cause the thing to spin. Using the right-hand rule, this force is going to cause it to spin that way. This force is going to also cause it to spin with that. So it's going to cause a negative moment. And so, but we know back on Earth, this thing isn't spinning. And so we must have a positive moment that prevents it from spinning, and that's internal. These the cut right here, like the has a moment in there. So you just draw the moment like that, and that moment is equal to, and if this is 3 meters, this moment right there is going to equal 33. So that's going to be 33 kilonewton meters. Sorry, it's not divided. So it's a moment is a force times a distance. Just like opening a door, I'm going to apply a force. And because this distance is this distance away from the hinge, just think moment is leverage. Moment is R cross F, and it is a vector. So here's your force, here's your distance vector. And so from here, you would start at the hinge using the right-hand rule, putting your fingers in the direction of the distance, and then sweeping in the direction of the force. And if this is a perpendicular angle, you get to multiply both numbers. So, and the moment is a vector this way. So that's the moment vector, and that's the direction of it. It acts through the hinges, and it has a magnitude of F times D. Cool. All right, and it's a leverage. So the farther this force is away from this distance, the more purchase you get, the more leverage you get. Okay, sweet. So that's where that moment comes from, and that's kind of this problem B. It wants to know, like, well, where would you put this to get the biggest moment? You know what I mean? So there we got a moment of 33 kilonewton meters, and so I really like to. The way that I like to do things is just do like a bunch of simple problems, because then you kind of get an idea of what's going on, where then you could actually make an equation for, solving for all values of x. You could figure out the moment of all values of x. We just took this slice at 3 meters. So now let's take the slice at 1 meter. So we're gonna come in here, have a 1 meter slice. We're gonna have 11 up. This chunk isn't moving. We must have to have 11 down right on this cut surface. It looks like we have a negative moment of 11 kilonewton meters. So we have to have a positive moment of 11 kilonewton meters. So now you can see if we put this thing in the middle, and where we're going to get the biggest, so we're going to get less moment at 1 foot. You know what I mean? So so maybe we'll get quite a bit of moment out where this thing is out there. All right, hell yeah. And so I think this is cool. Like, we're not solving the problem at all, but we're kind of just getting used to drawing free body diagrams. So now I'm gonna slice right here. I'm gonna slice at 1 meter over. So we have 6 meters and 1 meter. So sweet. So I'm gonna draw that, and we're gonna have this force P. We have 10 kilonewtons there. We're gonna have A is gonna be 11. Oh, okay, so now we're pretty much balanced. Cool, so, and this is going to be 1 meter, and this is going to be 6 meters. So we're pretty balanced, but we do have more force up. So now we're going to have a force actually down. We're going to have a force down of 1 kilonewton. And now let's see if our let's see if our moments are balanced. Well, obviously not. We have 11 kilonewtons this way and 10 and 1 going that way. So we have negative moments. So we're going to sum the moments. Where should we do this? It doesn't matter. Like, the only place that you can actually put a moment is right here. But like I said, you can sum the moments anywhere. So we could, well, let's sum them right here. Just because that might be the tendency. Be like, well, I'm going to apply the moment here. Why wouldn't I sum the moments there? But just know that you can apply a moment anywhere. That's the hardest thing. There is literature that shows that, hey, if you apply a moment to a rigid body, that moment, you can apply that moment anywhere and it acts the same. And I find that very fascinating. Cool. So we're going to sum the moments about here. We're going to have a negative 11 times 7. So we're going to have a 77. That's going to be in the negative direction. We're going to add it. It has to equal the positive moments. So we're going to, do we have any positive moments? Yeah, we have this 10. So we have, that's going to equal 10. Okay, these are not equal. So we have to have 10 plus what? So these are our positive moments. So we have to add a positive moment. So we're going to have this moment here, and that's going to equal 67. So we have a 67 kilonewton meter moment right there. So that's pretty sweet. And let's do it in 3 locations. Let's do it right here and then right there, just to kind of get a feel for if the moment gets bigger or smaller. So we're going to go 6 meters. We're going to have 11 and 10. And now let's kind of go a little bit faster. Obviously, this is going to cause a negative moment. To balance it, we have 11 up, 10 down. So we're going to have to apply 1 down right there. And so we're going to have an 11 and 11. So our moment right here, and it's going to be 6. So our moment right here, we're going to have this is going to cause a negative 66 moment. So we have to have a positive 66 moment. This moment's bigger. So now let's go to under 2p. So we're going to go 6. So we have 6 plus 2.4. So that's our distances there. We're going to have 10, 11, and then we have 20. Okay, so now this thing is going to go this way, so we actually have to apply a load right here. Alright, sorry about that. We got a new battery in. But hell yeah, I dig this, because this is just doing tiny things. Like, we're using one principle, like owning it, and then just doing it on repeat. You know what I mean? Taking another slice, doing the same thing. So we have 30 down, 11 up. If we had 30 down and 10 up, this would be 20. but we have 11, so this is 19. Does that make sense? So this is going to be 30 and then 30. So sweet. So these balance forces this way. Now we're going to sum the moments about this point. We're going to have positive 24, 2.4 times 10, and then we're going to have 8.4 times 11. And so that's going to be 92.4. So we have... this is going to be the positive moments. This one's going to be, so that equals 92.4. So the positive moments have to equal the negative moments, so we have to add a positive moment here. So 92.4 minus 24. And so we get a moment of 68.4. All right, so is that the biggest so far? 67, 66, 68.4. All right, sweet. So now let's actually take it 1 foot on the other side, just because we kind of want to know, like, hey, where's the biggest moment? I have no idea. So we're going to do 20 there. We're going to do 10 there. We got this 2.4, we got 6, and we got 1. And we have 11. All right, same thing. We have to have a 19 here. And now we're going to sum the moments. Now let's take a pause, because right here we had a big negative moment and then maybe a small positive moment. Here we're going to have a bigger positive moment, a bigger positive moment, and then but we're going to also have a bigger negative moment from this one. So let's see how that's going to work. So this negative moment is going to be this force times this distance. So I see 8.4, 9.4. So 9.4. So we have 9.4 times 11. So that's going to be my negative moment, 103.4. And I guess, yeah, let's just do this. That's a negative moment. No, I apologize. That's going to be a positive moment. My bad. Yeah, so, no, that's good. I don't know what my fingers are doing. So right hand, this is going to be a negative moment. So we have negative 103.4. We're going to add it to, this distance is 3.4 times 10. So that's going to be 34. Yeah, just 34. Holy hell. Okay, and then and this is going to be a positive moment. Should I add my calculator? 20 plus 20 times 1? Anyway, so it's fascinating how, yeah, just needing to throw in your calculator very simple things like 3.4 times 10 just to make your mind not fall apart. Okay, sweet, and that's going to equal 0. So obviously this doesn't equal 0, so we have to include a moment right here, a positive moment, and we're going to have 100. And so let's get this to the other side and then subtract both those. So we have 103.4, subtract 34, subtract 20, and we got 49. So the moment there is going to be 49.2. So that's pretty cool. I think we have satisfied that the largest moment is going to occur under that wheel. And so now we just need to know where to put that wheel to generate the largest moment. And so that's kind of interesting. And I'm totally going to do the mountain climber on this. You know what I mean? Let's do it. I mean, because we can, and because it's just good practice to do free body diagrams. So what we're going to do is we're going to put this right in the center. So we're going to, if this distance is 2.4, we're going to say this distance is 6, and 6 minus 2.4. This distance is going to be 3.6. So those are the distances on it. We want to find A and B. We're going to sum the moments at, we can just do sum of the moments at B are equal to 0. So we're going to say A times 12. So we're going to have, that's negative. So we're going to do 12A. That's my negative moments. I'm going to equal them to my positive moments. And so that's going to be 20 times 6. So that's going to be 60. Plus this one is going to be 10 times 8.4. So that's going to be 84. Sweet. So A is going to be 60 plus 84 divided by 12. So A is going to be 12 kilonewtons. Because these have to balance and we have 30 down, 12 over here, we must have, what do we need? 28. No, whole 18. Sorry about that. So 12 plus 18 is 30. We got 30 down, 12 plus 18. Sweet. So now we're going to figure out the moments at B. So let's draw this all the way till we hit this one right in the center. And so we're going to have that, 2P right there. P right there. We're going to have 12. I should have just drawn these in. So we have 10, and then we have 20. And, yeah, cool. So if we have 12 up but 30 down, we must have to have 18 up. Nice. And if we sum the moments right here, we're going to have 2.4 and 3.6. And this is 6 all the way to here. So we're going to have this as a negative moment of 12 times 6. So that's going to be 72. My negative moments are going to add to my positive moments. I only have one, and that's going to be 24. So I need to, 72 minus 24 is going to be 48. Oh, okay, so that's pretty wild. Because even just right there, that's weak sauce. We were generating a 68.4 moment when this was 6. You know what I mean? Where this distance was 6 meters, and that generated quite a bit. But putting this distance at 6 meters didn't generate as much. Yeah, that's kind of fascinating. But yeah, let's chop it under the other wheel just to make sure, like, we're good. So we're going to... No, that's not going to generate much at all. I mean, we could do it, though. We have 12 up, and we're going to have 10 down. That means we have another 2 down, and we're going to have 12 times 6. 12 times 6. Oh, so that is a moment. That's a moment of 72. And so that's going to be a negative moment of 72. Has to add to our positive moments. We don't have any. And yeah, so it's going to drive a moment. That's going to be a 72. M is going to be 72 in that case. So under that wheel, so if we have this at 6 meters, this wheel is going, under that wheel you're going to have the highest moment of 72. That's the biggest number we've gotten so far. So that's pretty sweet. Okay, so now instead of taking this at 6, which because if we do that, if this is the halfway is 6, we're basically saying this thing's right there. So let's not do that. Let's move this wheel at 5. So we're going to say this distance is 5, and then kind of do the same thing. But yeah, this is kind of cool. I mean, I think you can learn a lot from doing methods like this, of just doing the problem over and over again, but kind of in a different way. Because you will find places where your intuition was wrong. You know what I mean? I thought just like, well, yeah, that was kind of fascinating, that the biggest moment's going to be under that wheel and not that one. But when we had it over here, the biggest moment was under that wheel. Oh, and so I guess kind of the biggest moment is going to be kind of closer to the center than away from the center. So I guess I get that as well. All right, hell yeah. So let's just kind of continue on. So we're going to say this distance is 5. And we got 20. This distance is 2.4. And we got 10. And 12 minus 5 minus 2.4. And this distance is 4.6. So same thing. We have B and A. I'm going to sum the moments at B. So we're going to say 12A. That's going to be my negative moments. These are going to be my positives. So I'm going to say those are equal to my positive moments. And we got 7.4. So this is going to be 74 plus 5 times 20. 5 times 2 is 10. So it's 100. So we got 74 plus 100 divided by 12. And so A is going to be 14.5. All right, so we're good to go there because we're just going to sum the moments from A. And so we're going to have 14.5. We're going to go over to this 10. And so that's going to be a distance of 4.6. We're going to have 10 down. We must have to balance this, so we're going to have another 4.5 down. We're going to have a moment. So this one's going to cause a negative moment, so we must have to have a positive moment. So, and these don't generate. If we sum the moments about this point, these are in line with that point. They don't generate a leverage or a torque. So we got 14.5 times 4.6. Oh, this is less of a number, you know what I mean? So this isn't the biggest number we've come across, and we moved 1 foot that way, you know what I mean? So we can just, you know, throw in the towel right here, but that's going to be 66.7. Now let's, I don't know, let's go, just to make sure we're not doing things wrong, we're going to go 1 foot the other direction. So we're going to have 10, 14.5, and then we're going to have another 4.5 down. And so the sum of the moments from this point is going to be, we're going to have this negative, but then we're also going to have a positive. So this moment's going to be less because it's going to be 4. Well, not necessarily, because we got 4.6. So this is going to be 14.5 times 5.6 minus 10. And that's going to be 71. So we do get a bigger moment than 4.5 times 4.6. This moment would just be 66.7. So that is kind of fascinating that we are generating a bigger moment underneath the wheels. So let's go to the other extreme underneath this wheel, and we're going to have 20, 10, 14.5. So now we're going to have 30 minus 14.5. We're going to have 15.5. This distance is still 4.6. This is 2.4. We're going to have 4.6 plus 2.4. So we got 7. So we got 7 times 14.5. That's going to be my negative moment. So 101.5. This one from this point. And then plus 24. So minus 24 is 77. So we get 77.5. Okay, so we are generating. That is the biggest number so far that we've gotten. So yeah, so we kind of move this kind of closer to the center. Alright, hell yeah. So what we're going to do is we're going to take a step back, because in my videos, like, why I go through this is because you can have aha moments, you know, and be like, well, and maybe it's not obvious to you, but, you know, I mean, it's just for yourself. Like, wherever you are, you know, if you do like just a bunch of simple calculations, you see kind of patterns, and also it teaches you to be like, well, I don't want to just hammer out, you know, but you should be able to do this. You should be able to do like 10 calculations, you know, back to back, and then if they're simple enough, you're not going to make errors, but it's easier to see patterns, and then you can be like, well, yeah, let's try to analyze this. So we are going to go back to a simple beam where we just have one load on it, and so we're just going to put the load right in the middle, and we'll just use 10 kilonewtons. So we have 10 kilonewtons. That means that this is going to be 5 and 5, and so let's do that same process. And we're going to have 6 and 6, and let's chop this right at 6. Cool. So we're going to have 5 here. We're going to have a load of 10 down, and then so this is not balanced. We must have another 5 there. We're going to sum the moments about this point, and it's going to be a negative 5, and so we must have, a negative 5 times 6, so we have a 30. So in this case, we'll have a 30, negative 30, that has to balance with this positive moment of 30. Sweet. And the other way you can do it also is kind of interesting. This load acts right on this line of molecules, so we can chop it just in front of that line where, You know what I mean? So let's do that. So we're going to, and I'm just going to do that one right here. So we're going to have this 5 right there. That's not going to change. But we're not going to have a 10. We're not going to have anything right there. But right on the cut face, we're going to have a 5 down. And then you can see that the moment won't change. We still, if we sum the moments about this point, we're going to have a 5 times 6. And so that's going to be a negative 30. So we must have to balance it with a positive 30. All right, sweet. And now let's go a couple directions. Well, and then right here you can see that we could have summed the moments over here. If we sum the moments over here, these are gonna offset. So we would have a negative 60 plus a 30. You know what I mean? So then we'd have to have another positive 30 to couple it. This one, if we sum the moments about this, we're going to have a negative 30, 5 times 6, and we'd have to couple it with a positive 30. And again, we're chopping this, putting it in outer space. We're not seeing any rotation, but if we do have forces on it that are going to cause a moment or a rotation, we have to balance those. And then the sum of the moments are 0. So that's kind of how that works. Sweet, so that's going to be our moment right there. Now, kind of there was two things. I'm sorry to just kind of back off on the moment thing, but we need to figure out the shear forces and kind of what that means. All right, hell yeah. So I almost need to take a step back from my fundamental understanding, because I swear I looked at the back of the book at one point, 5 months ago in this problem, but I'm honestly, I don't know anymore. You know what I mean? Because one is that we put the load in the middle, the loads at the ends are going to be less. And so when it comes to shear forces, did we have any shear forces? Yeah, we had a shear force right here of 5. So that's the, along this cut section, this thing is going to want to shear across with a 5 kilonewton load. Now, if we get this load closer, so we're still just going to work with one load, and we put it at a quarter of the distance. So let's draw that. If we put that load at a quarter of the distance, this is 25%, this is 75%, this is 10. So what you're going to have is you're going to have 2.5 right there, and then 7.5 right there. So now let's chop this. Let's chop it right there, and so we're going to have 7.5, and we'll just chop it right in front. That's kind of an interesting thing to do. So we're going to have 7.5 kilonewtons down. Okay, so in that case, we're going to have a shear force of 7.5 kilonewtons down. Now let's actually chop it where we have 7.5, and then we'll have 10 kilonewtons. So this way we would have, right over that load, we would have 2.5 kilonewtons. That's going to be our shear. So it's kind of interesting. We're going to have the biggest shear right in front of that load. Where that got me thinking is if I put the 10 kilonewton load directly over point A, B doesn't see anything. And if we do a free body diagram, even if we chop out half of the length, we're still going to have 10 here. We're going to have 10 here. And, well, these forces are balanced, so we don't have any shear force. So if we put the load right over A, we're not going to have any shear force. So that's kind of interesting. But let's say we put, let's say it looks like this. So we have, this is point A, and we have a line of molecules here, and we put the 10 kilonewtons right over this line of molecules. And so just for intensive, this is 99.99% of the length is over on this side, almost 100, and then there's just 0.0001% over here. So basically 100% of the length is over here, 0% of the length is over here. So technically A still will have 10 kilonewtons on it. But in this case, we can take a free body diagram of this thing of molecules, because this 10 kilonewtons is on the second row of molecules. It's not on the first row. And so when we do a free body diagram of that first row of molecules, we're going to have this 10 kilonewtons up. We opened up a face, and so I should have drawn 3 rows of molecules, you know what I mean? So I would have another row, and I can just draw that in. So just pretend there's 3 rows of molecules here. And on the third row of molecules, we would have the 10 kilonewton force. We're just exposing 2 rows. And so, but this isn't balanced, and the only place that we can generate a force is on this cut surface. So we're going to have a 10 kilonewton force down, and that is a shear force. You know what I mean? So that is the shear force. So the biggest shear force you can generate is when this load is as close to A as possible, but just a molecule away, because you're trying to shear molecules away. That's the only reason this problem makes sense, and maybe I'm missing something about that, but no, if your load is directly over your support, you don't have any shear force. You're just scrunching down that molecule of material. But if you go a molecule over, and that's where you put that shear force, well, hell yeah, because under A is going to feel all of it as a percent. It's going to be a little bit less because, you know, technically B will have some. B won't be 0, but it'll be very, very close to 0. But yeah, so that's why this problem makes sense, is because you have this dolly, you know what I mean? Because when you put P over A, well, cool, you know what I mean? You don't get any shear load from P, but you generate 20 kilonewtons of shear as close to A. Well, you're trying to get the load as close to the supports as possible without going over. And so, yeah, so that is fascinating, where, I don't know, is this problem set up wrong, where wouldn't the biggest shear be where you take this 2P directly over B, but not directly on top of it, just one molecule to the side? So let's do that, because this problem is freaking me out. So let's do the 1 over A first. And so, and I think we already solved for that. We know that 2.4 divided by 12 is 20% of the distance. So if we take P over A, A will see 10, it'll see this, plus it'll see 80% of 20. 0.8 times 20. So it's going to see 26. So in the case that this is over this side, A will be 26, and then B would be 4. Okay, sweet. And then we're going to do this scenario where, like, we're going to chop out two rows of molecules, and we got A is 26, but we have P is going to be directly over A, so we have 10 right here. And now we're only going to have a shear force. We need to put a shear force down of 16. Cool. So that's going to be the shear force there. So we'll have a total shear of 16. However, if we said that we didn't put, like, you know what I mean, you had, instead of P being directly over A, you put P, so it's just almost up to A, on the third row of molecules, and now we're just exposing 2 rows. So we're going to have 26 here for A. We're not going to have anything down because that this P is going to be on this third row of molecules. So now you're going to have a shear force of 26. So you'd have a 26 kilonewton shear force. Yeah, so that's fascinating to me that seems to be. So there you go. So there's one option where your shear force is 26 kilonewtons. So now let's go to the other side and do the same thing. B is going to see 20 kilonewtons from this 2P plus 80% of 10, which is 28. So cool. So you're going to see 28 kilonewtons over here. But I think this is where I don't think they intended this problem, because if this 2p is directly over b, you're not going to generate any shear. You're just scrunching those molecules down. But like what we're trying to say is that there's a row of molecules here, and 2p is acting on the next row. So these molecules are getting sheared. There's going to be no distance. I mean, technically, it will be over b, but it'll just be like slightly. And we generate the biggest, so far we're up to 28 kilonewtons. So we're going to do a free body diagram that way of those two rows of molecules. We're going to have 28 kilonewtons up. We're not going to have any down force because this 2p is on the third row of molecules. And so that means that our shear force is going to be 28 kilonewtons. So there you go. So this problem, I'm gonna throw a wrench in, and maybe I'm just overlooking it, but I would say x is a distance of, that's where x isn't a distance of 12 meters. It's where this is at b. But I would say, and then so you would have 12 meters minus this distance of 2.4 meters, and so that's going to be 12 minus 2.4. 9.6 meters. But if this is directly over b, you're not generating shear. You know what I mean? You're just scrunching that last row of molecules. You're generating compression. This has to be 9.6 meters minus one row of molecules. So for a technical and what does it say? Determine the distance x that will produce the maximum shear force in the beam, and also determine the maximum shear force. So the maximum shear force would be 28, and it should be at a distance of 9.6 meters. But minus one row of molecules. Cool. All right, hell yeah, hell yeah. So I think I'm satisfied there. So I'm glad I went back to shear, and now we can go to the moments. And then I was just interested in moments because it seems like the biggest moment's going to be generated when your force is basically in the center of the beam. If your max force is in the center of the beam, you're good to go. But since we have two forces here, now if these were equal, if there was 20 and 20, then hell yeah, you would just put this thing right in the middle. So what we need to do is also treat this like, hey, where's the like, what am I getting at? Like, where's the center of mass? And that is interesting. Yeah, you could do that. It's like, if I have this thing floating in outer space, just this thing, that's all I'm doing right now, and we put 20 kilonewtons there and 10 kilonewtons there, where do I have to apply a force? Like, I could obviously balance it with 10 and 20, but where do I get to apply one force where this is going to be 30 and it's not going to spin? Well, we've already gone through this. Is like it's balanced when, like, hey, it's just upside down. Because let's do this upside down and say, hey, this support's going to take 10, this support's going to take 20, and I have a 30 kilonewton load. The only way this makes sense if it's not spinning is that, well, this is going to be 1/3, so we got 33% right here, and then we got 66.6% right there. And so we would say that if this is L, that this would be 33.3% of L, and then this would be 66% of L. Cool. So so I think that is going to be a place that gets the most juice. So yeah, let's run through that and just see if that's the case. So that would be at a distance. Where would that? So what would? Yeah, and what are we trying to get at? Well, we want this distance. We want this load right there to be right in the middle of the beam. Cool. So to do that, well, what is this distance? 2.4. So we got 2.4 times 1 divided by 3. That's going to be 0.8. So right here you'd get 0.8 meters, and right here you would get 2.4 minus that. 1.6. Cool. So, yeah, and it's fine. Like, I'm totally satisfied doing these problems from an intuitive perspective, running through a bunch of calculations, and then just, you know, just kind of intuiting what the answer is. All right, sweet. So yeah, I think this should be the answer, hopefully. All right, so we are going to say that this is going to be the center of the beam. This distance is going to be 0.8. This is 1.6. If this is the center, we got 6 minus 1.6. This is going to be 4.4. And then we got 6 minus 0.8. This is going to be 5.2. So I think that's going to be where the biggest moment's going to be generated. Now, I don't know if the biggest moment's going to be right in the center of the beam. Who knows? But might as well go there first. So if we put the loads here, we're going to sum the moments at B. And that's going to be equal to 0. So we have 12A. That's going to be our negative moments. We're going to add them to our positive moments. So we got 5.2 times 20. 5.2 times 20. So that's going to be 104 plus 10 times 2.4 plus 5.1 plus 5.2. 76 plus 104 divided by 12, and we get 15. So A is 15. B must be... oh, and in that case, that's pretty cool, because that's where B is 15. Because that was the other, thing that I was going to intuit. I didn't want to say, because I didn't want to go down that road. But I figured the highest bending is when that these were going to be the lowest numbers they possibly could. Now, I don't know. Maybe you get into a scenario where these can't be equal. But that makes no sense. I mean, obviously, if this thing can travel across this beam, there's a point in here where these are both going to be equal. And I was just intuiting that where these are the lowest values, where this one's 15 and this one's 15, you can't have them both be lower values. You can have one be lower, but the other one's going to be higher, and that's where you're going to get more shear and less bending. But where these are taking equal loads, that's where you're going to get the most bending. Okay, cool. So now we're going to, well, yeah, let's go right to the center. So we're going to have 4.4. We're going to have this 10, 1.6. You're going to have 15 there. And it must mean that we have another 5 down. So we have 5 down in shear. And then the moments, sum the moments here, we're going to have 4.4 plus 1.6. So we're going to have 6 times 15. So we're going to have negative 90, or 90 in the negative direction, equals 16 in the positive. So 90 minus 16. So we have a positive moment of 74. I don't know if that's the biggest number we've come across so far for our moments. I think we generated a 77.5 in this case. So, and in this case we were 4.6. You know what I mean? So right here we're only 4.4. Okay, so that doesn't generate the biggest moment. But now let's go right under P and then just do kind of a bunch of these. So we're going to have 15, 4.4, and let's say we're just to the side of P where P doesn't, well, no, let's just do the 10. 10, and then we're going to have another 5 down, and we're going to generate 15 times 4.4. So that only generates a moment of 66. So, okay, so now let's go all the way over to this 2P. So we're going to go all the way over there. We're going to have 15 up. We're going to have 10 down. And now we're going to have 20 down. And so we have 30 down, so we must have 15 up. We sum the moments about here. We're going to have this distance of 4.4 plus 2.4 times 15. So we're going to have 102, And now we're going to subtract this distance of 2.4 times 10. Subtract 24. All right, so that gives us the biggest number, 78. 78 is our biggest number so far that we've generated. So I think that's going to be, yeah, that's pretty wild. So this was right at the midpoint, 74. This was where, yeah. So, and now it's just like I don't want to do it, but what we're going to do is we're just going to move this thing a tenth of a foot. Like, what direction should we move it? I think we should move it in a tenth of a foot, run the calculations, and then move it another way a tenth of a foot and run the calculations. So even though it's kind of a pain in the butt, like why would anyone, do that? Because what a maybe waste of time. But no, we're good. And so we're gonna go 4.5. There you go. That's all. That's the only value we actually need. So we got 4.5. This is 2.4. 12 minus 4.5 minus 2.4. So this is going to be 5.1. Okay, sweet. So we're going to sum the moments at B. So we're going to have that 12A is going to be equal to 5.1, 2. Oh, it's really hard for me to do simple math. All right, so we're going to have 75 plus, this is going to be 20 times 5.1. And 75 plus 102 divided by 12. And so A is going to be 14.75. B must be 30 minus that. See, why would I do this? Why can't I just do this simple math? But anyway, since I don't want to make simple mistakes. All right, so and now we're going to do our free body diagram. And we're just going to go right to the source. We're just going to go right to this 2p. So we're going to have 14.75. We're going to have 10 down, and then we're going to have 20 down. And so we're going to have 30, and so that means we're going to have an upward force of 15.25. Yes, this is smaller now. So we basically have the same setup, but we do have a little bit bigger distances. All right, so let's see if this generates any more. So the negative force is going to be 4.5 plus. So these two distances added, multiplied by the force, times 14.75. I'm going to store that as x. And then we're going to subtract this 24. And we only get 77.775. So we can stop already. Okay, so now we're going to go the other direction. Instead of a distance of 4.4, we're going to do 4.3. So we're going to go 4.3, 2.4. All right, and this is going to be 5.3. Okay, sweet. So now we're going to sum the moments of B. All right, hell yeah. So, yeah, we're going to sum the moments at B. So, let's see. Obviously, we're going to have A is going to be 12A. So that same thing, and we're going to have 10 times 5.3 plus 2.4 times 10. So we're going to have 77, and then this one is going to be 20 times 5.3 is 106. So we have 183 divided by 12. All right, so now we got 15.25. So A is 15.25. B is 30 minus that, 14.75. All right, let's do the free body diagram all the way to 2p. We're going to have 15.25. We're going to have 10, 20, and so we're going to have up of 14.75. Okay, so now our distance, what is our distance smaller? Yeah, hell yeah, our distance is way smaller. In the ideal, our distance was 4.4. So let's just, yeah, anyway. But this is going to be so yeah, let's do it. So we're going to do 4.3 plus 2.4 times, we're multiplying by a bigger number, so maybe this does give us a bigger number. I don't think so. And then minus 20. Oh, it does. So this gives us, oh, hell yeah. I'm so glad I did this. Because who knew? Yeah, I didn't. Yeah, maybe I just didn't think there was any rhyme or reason to this. you know, I had a hypothesis that, you know, the center of mass of, I mean, the center of weight of this, you know, would generate, I don't know. But yeah, this is getting a bigger number. Sweet. Okay. Yep. Oh no, minus 24. No. I apologize. Nah, never mind. So yeah, I'm glad I caught my error, because I think we're on the right track. This should still give us a smaller number. So we have 4.3 plus 2.4. That's going to be the distance, and multiplied by this 15.25. Okay, so that's going to be our negative moment. We do have a positive moment here, but it's 10 times 2.4, so it's minus 24, and we get 78.175. Now, is that bigger, though? Because here we got 78, and I thought that was the ideal. This was 77.75. This one was 78. Huh. And it makes me think, is like, hey, could we, could we reduce this, you know, just take our cut at 2.3. So yeah, let's try that one. So here, instead of taking our cut right at under 2p, we're going to take it 0.1 meters this direction. So our shear forces are going to be the same, but our moments about this point are going to be different. It's going to be 15 times 4.4 plus 2.3. And then we're going to subtract 23. 77. No, so that doesn't help. Yes, this is interesting. We are getting a higher number. Damn. So so it makes me think that we actually need to come up with an equation to solve the location of this. Alright, but before we do that, let's take this example. We got a bigger number, but let's take this example and cut it at 2.3. So we're going to take it in, and so we're going to have 4.3 plus 2.3 times 15.25 minus 23, and that gives us a lower number. So at least if we run an equation, we know the highest bending is going to occur right under this heaviest wheel. And so so now, yeah, I'm satisfied. I think we can do an equation. Let me burn off some more paper. All right, hell yeah. So we're going to try to do an equation for the bending moment based on this variable x. But I was just like, man, I thought I had it dialed in, and I don't know, I kind of want to ponder, you know, how to make a simpler problem. You know, like one is you could make this thing, you know, L divided by 2. So, you know, if P was over here, 2P would be right there, and obviously that would be the distance to cause the biggest bending moment. If you went the other way, that wouldn't cause. But then if you went in between, like, I don't know, do you generate, if you move this just a little bit, the fact that that one's there, do you generate any, you know, extra bending moment? I don't know. So this is kind of fascinating. So maybe we'll just learn something by trying to run the equation. So we're just going to pick a generic x, and we're going to sum the moments about b. So we're still going to have 12a again, and then we're going to have our positive moments are going to be maybe we shouldn't do it this direction though. I mean, if this is our x value. So yeah, so we're going to sum the moments about a. So we're going to have 12b is going to equal, here's our negative moments. So we have px plus 2p times x plus d. Okay, sweet. So now we need to solve for b. And b is going to be just all this divided by 12. To save writing, I'm just going to do that. Sorry about that. But yeah, there's b. And then a is just all this is 30 minus all that. Alright, sweet. So now in this scenario, let's see, are we still going to... A is just 30 minus all that. So we can still take our free body diagram from A, and then we're going to take it all the way up to 2p. So we're going to have p right there, 2p right there. We're going to have this distance x and distance d. A is going to be all that. A is going to be 30 minus b. Cool. So it's just going to be all that. So we have A right there. And then we're going to sum the moments about here because we don't need to find the shear force. You know, the shear force is going to be whatever, who cares, but we are going to have a moment. And so that moment, summing the moments about this point, are going to be the distance x plus d. So we're going to sum the moments about A is equal to 0. So let's do that. So we're going to have a distance x plus d, and then multiplied by A. That's going to be the negative moment, and that's going to equal the positive moments. So we're going to have that equal to PD. That's it, PD. Cool. So now, we can just put this into our calculator and solve, well, and then graph for x. So let's get everything to one side. So we're going to go 0 is equal to x plus dA minus PD. And then we're going to just write it all out. So we have x plus d, and then A is all that. A is 30 minus, and then we have this, px plus 2p x plus d. And I don't care if it's, you know, ugly. But yeah, that's A. And then we're going to subtract PD. And then we're just going to throw it into our calculator. Just make sure we got all the terms. But I just didn't want to do something like this first. If you do something like this first, you're not gaining any knowledge from the problem, and you might make mistakes. Alright, sweet. So, yeah, let's clear all this out. Yeah, so alpha P is 10, alpha D 2.4, alpha L 12. Alright, so we're set. So we're going to go x plus d, parentheses 30 minus px plus 2p x plus d. Alright, and then divided by 12. Sweet. Another parentheses minus alpha pd. And what is this an equation of? Moments. So yeah, we should have a force and a distance. We got that. This is going to be a force, and then we're going to multiply by a distance. This should be, if this is a distance, this is a force times a distance. We must divide by a distance, and that's what we have. That distance 12. This is L. Cool. All right, so now we're just going to graph this and then see what should it tell us. Yeah, so we're trying to get we're going to zoom out. We're trying to get a slope like this, so it should hopefully be a parabola. Huh. Yeah, what's our distances? X, -1 to 12. Our y is going to be, what are we solving for here? We're trying to solve for this distance. And yeah, it's where the x crosses the 0, or where x is 0. That's where this is going to be satisfied. This equation. And so yeah, I don't know, y I guess can just be, so we're going to go -10 to 200. Sweet. So we got, yeah, so we got it. So we're going to go to our maximum value, left bound. And this is the does this make sense? This is the equation where the moment is going to be maximized. Is that true? I have no idea. Like, this equation looks ridiculous. Oh, okay. No, I totally forgot to put the most important part of this equation in, because this is some of the moments. This is going to be the positive moments. Or no. We said this was going to be the negative moments is equal to the positive moments. But we know we're also going to generate... We know that these from all our calculus, this is going to be like way bigger than this. So we're also going to have this plus m. And so this is not equal to 0. This is equal to the moment. So this is equal to that positive moment. So there you go. So the y value on this. So we have y is equal to whatever x. Y is the positive moment. And then x is that distance. You know what I mean? So that distance, x in meters. That's x. Sweet. So holy hell. I was just like, yeah, I couldn't figure out what this graph was. All right, so there you go. X is 4 meters. So when x is 4 meters, man, and is that going to make sense? We got 4 plus 2.4. I don't know. You know what I mean? And so when x is 4, this is 2.4. Halfway, so this is going to be 0.4 and then 2. Yeah, what percentage? So if we have 2.4, so if we have 2 divided by 2.4, that's 0.83, 83%, and then we got 0.4 divided by 2.4, and that's 16%. So, yeah, so it's kind of fascinating. So it's not where the midpoint of the force would be between these, but yeah, it is going to be closer to, yeah, what I did is just find the midpoint, and then this is 0.4 from the midpoint. So if this heavy weight was directly over the midpoint, you can get more juice by moving it this way. But I think you just have to go by the moment equations. Like, for whatever reason, I can't rack my brain is exactly why. And this value is going to change. This 16% of this distance 2.4. Making this moment the biggest will change depending on, like this 2p versus this p. If these were the same, obviously this distance would be 50-50. But it's just interesting how one increases, one is half the other, and then this is your ratio between those distances. All right, so sweet. So now let's use that to our knowledge and go back and just hammer out. So we're going to set x is equal to 4. We got 2.4. And let's just run through the process again. So we have 12a is equal to, now this is going to be 12 minus 4 minus 2.4. This is going to be 5.6. So we have 12a is, so we got 5.6 plus 2.4 times 10. Holy hell. And maybe I was, hopefully I didn't do anything. No. I feel like I was multiplying the wrong ones, but no, I think we're good. Plus 5.6 times 20. All right, so we have 192 divided by 12. So this gives us 16. So A is going to be 16 kilonewtons. So that means B is 14 kilonewtons. All right, let's do our free body diagram all the way up to 2P. And we're going to have 10, 20, 16. It doesn't matter what the shear forces are. So let's not even do those, but we're going to have 4. So we're going to have 6.4. 6.4 times 16. That's going to be our negative moment minus 24. And that's going to give us a moment of 78.4. That is part of the question. They want to know the maximum bending moment, 78.4 kilonewtons. And that's the biggest number that we got. We got 78 right there. Yeah, that was pretty cool. What we thought was going to be the highest was, Oh no, we thought this 4.4 was going to be the highest, but then we went to 4.3 and we got a little bit higher. And you know, I just wasn't going to do the mountain climber all the way down to 4, so that's where we busted out our calculator and then did an equation. And now we can see that this is 28.4. And just to double check, we're going to go to either side of it. So let's do 2.3, 10, and then 16. And we can see that if we sum the moments about here, we're going to have 4 plus 2, oh sorry, whoa, I don't want to, anyway. I got to check this graph. Hopefully I didn't ruin it. No, we're good. So we're going to have 4 plus 2.3 times 16 minus 23. So that's going to generate 77.8. So obviously that's not a bigger moment. Now we're going to go the other way. We're going to go 0.1 meter this direction of 2p. So we're going to have 20, 10, we're going to have 16, and we're going to sum moments about here. So we're going to have 4 plus 2.4 plus 0.1 out to this 16. So that number is going to increase, but now we're going to subtract 25 because we got 2.5 distance times 10. And then we're going to subtract 2. And that gives us 77. So yeah, so the biggest bending is going to occur right under this wheel when x is 4. And when that wheel is a distance of 6.4 from A. All right, hell yeah. So, man, that was pretty cool. And it's good just to do reps. All right, hell yeah. So now let's do the part that I really don't want to do. Now that we know that x is 4 for this one. It says we need to draw the bending moment diagram. And probably the shear diagram as well. But no, it just says draw the bending moment diagram. And I think, holy hell. So, yeah, and let's just do our mountain climber approach, you know, just kind of hash it out. So, we know that when x is 4, A, what did we say A was going to be? Well, let's do it. So sum of the moments at B is going to be 12A. That's going to be negative equal to these moments. We're going to have 4 here, 2.4, 12 minus 4 minus 2.4. This is 5.6. So we're going to have 10, 2.4 plus 5.6 times 10 plus 20 times 5.6, and then 12, that divided by 12. Cool. So A is going to be 16, B is going to be 14. Alright, so now we're going to, might as well just take it at 2. So we're going to do 2 meters, we have 16, and then we don't have anything here, but we have 2 meters, and so well, we're going to have a shear force of 16. This is we're going to sum the moments about here, so we're going to have 16 times 2, and then we're going to, what are we going to do? Yeah, this is going to be, we need a positive moment of 32. So we know that at x is equal to 2 meters, we need a positive moment of 32. If we go to 0, we're still going to have a 16 kilonewton force here. We're going to have a 16 kilonewton force down, but this is going to happen on the same row of molecules, so we're not going to generate any moment because there's no distance. So technically that's going to be 0. We just need to see if this is linear. So now I'm going to go up to 4. So I'm going to take this chunk up to 4. We're going to have 16, and we can totally see that it's linear. So we take the moments about here. It doesn't matter what shear is going on at all. Our moment is still 16 times 4, and that's going to be a negative moment. We need a positive moment of 64 at x equals to 4. Okay, hell yeah. And that's either side of this. Now let's go to 4.1. So we're going to go to 4.1 meter. And we are going to have a 10 down here. And we're going to have a 16 up. We're going to sum the moments about here. So we're going to have 4.1 times 16 and minus 1. So this is interesting because we have a spike. Do we have a spike in the moment? I don't. No, we're just 64. So right here we're going to have 64.6. But now, yeah, let's take this down to like 0.01. And if we do that, we're going to have a moment of 4.01 times 16 minus 0.1. And so we're approaching 64. So yeah, so we do it is continuous. It's not discontinuous. But now we need to figure out what the moment is from 64 to here. And so let's just do that. So we're going to go 4.24. So there's 4. This is 2.4. We do have a 10 down. Whatever we have here doesn't really matter because we're going to sum the moments about here. So it doesn't matter what force is applied. That's 20. It doesn't matter what shear force is needed to balance this. But if we do a 16, we'll obviously need this to be 15. But we're going to sum moments about this, so this is irrelevant. And we're going to have 6.4 times 16 minus 24. And we get 78.4, so sweet. So there you go. So we're going to have 64 to 78.4 in 2.4. So we can go 78.4 minus 64 divided by 2.4. And this is going to be 6 kilonewton meters. So it's going to be an increase in the per every 1 meter. And from A to 4 meters, we're going to have 64 divided by 4. So that's going to be an increase of 16 kilonewton meters per meter for every 1 meter. So yeah, so our slope on this, from x, we're going to, what am I saying? Our moment, the bending moment in each of these chunks is going to be more and more and more up to this point. You are going to increase up to this point, but just at a smaller slope. And then once we get to 78.4, then we're going to probably go back to 0, because let's take the bending moment all the way to the other end. So we have 5.6, we got 20, we got 10, we got 2.4, and we got 4. And we have 16 up. It doesn't matter what we have here, but obviously we're going to have 15 up. No, I'm sorry. Did I say, shoot, this should be 14. 16 plus 14 is 30, balances those forces. But like I said, it doesn't matter what's happening here because we're going to sum the moments from here. So we're going to have this negative 16 times 12, so 16 times 12. And then we're going to subtract 2.4 plus 56, or this distance, 5.6 plus 2.4 times this 10, and then we're going to subtract, this is 20, subtract 20 times 5.6. All right, yeah, so we don't have any moment there. So sweet. And it's going to be linear. So we're going to go from 78.4 back down to 0. And so, hell yeah, 78.4 minus 0, so that's going to be the change over 5.6. So divided by 5.6. So that's going to be a negative. So we're going to change by 14 kilonewton meters per 1 meter. You know what I mean? So that's going to be the slope downward. Okay, so now using those values, we can I don't know, draw the graph, I guess. So yeah, I might as well make it nice. Oh man. So we're going to just do that, and then we're just going to hit these points. Now it's not going to be to scale because this distance is 4 meters, this is 2.4 meters, and this is 5.6 meters. And you can obviously see that we need to move it that way just a bit, for sure. And all right, so up, so yeah, and then so we're going to do our moment diagram. And I'm going to move it down here because maybe we want to do the shear diagram the same way. So here's our moment diagram. We're going to start at 0, and it's all going to be a positive moment, the entire thing. And so we're going to go up to 64. We go up to a total of almost 80. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. And then we got up to 64. So 1, 2, 3, 4, 5, 6, 64. So we're going to be right there. We're going to go up to 78. It's going to be right there. And then we're going to go back down to 0. So this is going to be 78.4, 64. And there's our moment diagram. Now this is one of those problems where it's just like, man, it'd be sweet to have one equation to, you know, find all the different moment diagrams, you know, that, yeah, it was fascinating. We had to figure out what generated the biggest moment. But yeah, even we had to figure out that the biggest moment was going to be generated right under that wheel. I wish I knew better ways to just, you know, figure out an equation to be like, well, obviously, and or maybe an equation that tells you exactly where that moment's going to be the biggest using maybe a different equation. All right, so there's our moment equation. And now let's put this aside because maybe we do want to find the shear equations and see why this is the way it is. So we're going to have 16 there, 14 here. And again, if we do any sort of slices, we're going to have 16 up, and we got to balance it with a 16 down. And so, and this is where your moment equation, you know, is going to be negative. And I never really liked that, and I can't explain why the shears are going to be negative. I think it's because this being negative right here is actually called positive shear. So we're going to get a negative value of like negative 16, you know, all the way up until this P. Yeah, I don't know. Yeah, let me look up the sign convention on this. All right, hell yeah. So yeah, if we're going on this side, you know, doing our free body diagrams and finding the shear on that side, that is a shear that's a positive shear. You know, and if we went from B over to this way, we would have an upward. You know what I mean? So we would have that, and that would be. But both of these indicate a positive shear. So let's keep that in mind. So this negative 16 is because of where it is. It's going to be positive 16. Cool. And if we go all the way up to P, we're going to have a positive 16. But once we get to P, we're going to have 16 here, and then we're going to come down with 10. So then we have to have a shear force of 6 newtons down. So we're going to have, even though this is in the negative direction, yet due to that convention, this is a positive 6. Cool. Now let's take one all the way over to 2P. And so we're going to have 10 down, 20 down, 16 up. So now we're actually going to have 14 up. And this is going to be a negative 14. So that's where our shear graph really goes the other direction. And yeah, that's fascinating. Alright, my brain can't handle it, but this is where I want to spend my time like researching, because it's just like, I mean, I don't see a visual representation. I mean, I get coming on this side where, yeah, you're kind of like shearing this down, but then why it switches, for the life of me, I have no idea. But anyway, let's just run with it. And so we have negative 14, and that's going to be negative 14 all the way to there. So sweet. So now we can grab our sheet of paper, and so we're going to do a shear diagram. And sometimes it's just good to just, you know, go with the convention. And yeah. All right, so this is going to be, we're going to do 5, 10, 15. And so the first one's going to be 16. So we're going to be right to there. Then we're going to be at 6. So we're going to be right to there. And then we're going to be, oh, bummer. I kind of drew this wrong, because we're going to have negative 14. Man, 1, 2, 3. And then so this one's going to be down here. Alright, it's going to kind of get in the way. But there you go. So negative, positive, positive. Alright, booyah. So there is the shear diagram. And then here's the moment diagram. And does this make sense? I mean, does I don't know, when it comes to the slopes of things, is this 16, because this is 16, this is 6, and this is 14. Alright, hell yeah. And it is, because we have 64, increase of 64 divided by 4 meters. And so yeah, that's going to be a shear of 16. So that constant shear over at this distance is causing that moment. Cool. And then we are going to have still more, but this 7... Alright, hell yeah. So I'm glad I took a pause, because we're going to finish the video, but we are going to tackle, I mean, there's no reason, we understand like this bending moment, you know what I mean, that makes sense. If you put it in the middle, more bending, and if this is out to the side, this thing's not going to bend at all. So, but then the shear, why is the shear so hard? You know what I mean? And so if we have this weight out here, I think I just have to go back to kind of the free body diagram of like if we cut out this little chunk, we are going to have an upward force on it, and to balance it, that means that we're going to have a downward, you know, kind of a downward shear force. And if we think about that, is that, hey, this side is maybe supported, and then this side is trying to shear it this direction. You know what I mean? So maybe that's just one visual, is especially when you're driving across a bridge. If this is a heavy car, this part of the bridge is secure, but then your car is going to bring this bridge down on this side, and then you're going to shear those layers like that. Now, then why is the shear negative over here? So that was the other thing that I was just like, well, I need to be able to mentally explain that. Alright, holy, this should be super easy. I don't know, but nah, I mean, this is kind of wow. So, you know, there is nothing, there is no car right here, but there is a car right here. And then this car is going to be lower, and it's going to shear in that direction. I don't know, maybe that's one way to look at it. And so, alright, one thing that's driving me nuts is the fact that we have to reverse, like the signage on this. This is, so this, I mean, if we did this, this is up, so this would be, you know, we have 16 newtons here, and then we cut out this chunk, we're going to have 16 newtons down. We're just by convention, we're going to call it positive. But I think oh man, I mean, this is why you should talk through things. Just because you're going to make errors, but you're going to get closer to the truth. So, yep, if we do cut this chunk out, all the weight is over here, and we do have an upward force holding this chunk, but we are going to have a downward force, you know what I mean, like shearing it in this direction, and that's going to be the positive direction. And that's why we have positive shear. But when we get over here, we must have a shearing force in the upward direction. And the reason we have that, and why it's different than this little chunk, because this little chunk doesn't have any weight on it. It's being supported over here and trying to maintain that position. All the weight's over here, and obviously that's trying to pull it down. And so that's where we get this downward acting force on that face. So let's see if that makes logical sense now that we take a chunk all the way out here, which includes this weight. So we would we would say that this now this thing is hella heavy. It's not being pushed up. Like over here, this thing was being pushed up, and then the weight the weight was over here. So we had that that shear going this way. Over here we have, this thing is kind of, I don't know, I think it might be good to just visualize that if all the weight is right here, it's going to be moving down. And on this face, we would need a, we would need an upward to sorry about that, but to keep this thing stationary in outer space, you know, just in space, so it's not like moving. We have all the weight on this side. We definitely need an upward force, and so we're going to be applying an upward shear, and just by convention, this is the negative direction. Anytime that you have something out here and then you're driving an upward force on it, then that's going to be a negative shear. So, man, I'll have to work on that, but that was the best I got. And, yeah, but yeah, I think bending moment's way easier to figure out, but just shear, because you have a positive and a negative, and you're like, what does that mean? And I'm sure it's fairly simple also, that if I have this chunk, let's take a look at this. If I have that chunk, and I have this row of molecules, does that, and we have this downward shear, does that mean that this row of molecules is wanting to move down? Yeah, I could see that. And I could see it way better as if this was like rigidly attached, you know, to the wall. And then you have like this heavy car out here on a cantilever. And then we're just analyzing this chunk. That I could for sure see, where you would have, you know, this chunk wants to move down. So now let's take it to the other side. And I think you just take it to the other side just by making a cantilever this way. And then all the way out to here. And then, well, darn it. Alright, so in this scenario, this had the weight. And now we need to make a scenario where we're taking it all the way out here. And then this side has the weight. And it's going to be lower, and then this side is going to be higher. So I don't know, maybe that's just a very simplistic representation of kind of what's going on there. And then I just need to get better at maybe adopting that this is positive shear. You know, if I have a chunk of steel and then I support it, you know, rigidly, and then I want to, like, move it like this. So I'm going to move this side down. That's going to be positive shear. So maybe if I have a chunk of steel and then I move it where this side moves down, that's going to be positive. So this, I don't know how you're going to figure out, like, you know, your own method to figure out why this is positive shear, what sign convention works. I'm sure there's some tricks, I just don't know them. But if I wanted to do the opposite, if I had this chunk here, but I wanted to move it up, so I'm gonna brace this chunk, but then I'm gonna come in underneath and then apply a force, and this is going to move that way. Yeah, maybe that's the less intuitive, you know, especially if I'm holding this chunk on the left. Like, hey, moving that up, yeah, that's kind of not the simplest way to shear something. Like, obviously, if I was holding something, I would probably shear it like this, you know, move the right side down instead of go the other direction. So just right hand dominant, I'm going to pull down on my right hand to shear this pen. I don't know, so you're just going to have to come up with your own conventions to figure out why. But it is two different things. So when we do have this negative shear, that's going to be, you know, pushing up on this side. And this side is going to go up. This side is going to go down. And hell yeah, because we got a heavy weight over there. So if we take a cross section right there, yeah, this side is going to be more weighted. And this side is going to, you know, like split up like that. And you're going to have a fracture like that. If you're going to have a fracture, it's going to be in that direction. And because you can have, especially when you're going to break things, if you break, I know if you take a crayon, and let's do this to make this video more exciting. Alright, hell yeah. So we have a crayon, and this is going to break in 3 places, and it's kind of fascinating. I'm going to put a bending moment on it by putting a couple on both fingers, but I think what happens is that it's not a true bending moment. So let's kind of draw a diagram before we actually rip this thing in two. or actually 3 pieces. Because it would basically be like having a bridge, and instead of applying a moment on both sides like this, we can't do that ideally. So what we're going to do is we're going to apply an upward force there, an upward force there, and then downward forces there. And so this is the scenario that we get into, and I actually should model this. Oh, I guess it did break in, but it should break into 3 pieces, so let's see. Oh, it's not doing it at all. Holy hell. Alright, sorry about that. No, the experiment was this, is if you actually shear this. Yeah, we're not even talking about bending at all, we're talking about shearing. So if I try to shear this, kind of the same thing is maybe I can't do it ideally, but if I try to shear this like this, in this direction, it's going to break into 3 pieces. So let's do it. No, I guess it didn't. Bummer. Alright, one more time. Let's see if we can break it into 3 pieces. There you go. So yeah, shearing it breaks it into 3 pieces. I don't know why that is. Be fascinating to run the numbers. Alright, let's see if it works with a piece of chalk. So we're going to try to shear it. Yep, so you get 3 pieces. So I think it's due to, because the material is brittle. When you try to shear it, it breaks into 3 pieces. I do not know why, but it's kind of fascinating. Hell yeah. Alright, hell yeah. So I think we're done with this problem. Man, so thanks for joining me, and guess what? That's a video.